Okay, let us start the course formally. This is ME321 Advanced Mechanics of Solids. This course will be taught by me. I'm Sumit Basu. And part of the course, about 2.5 weeks of the course, will be taught by Professor P. Venkatnarayan. This is mostly going to be the experimental part of the course. Since we have gone through this preliminary meeting and we know what the course contents and the evaluation policies are, I'll skip all that part and let me go straight ahead to the objectives of this course. The main question that I'm trying to answer here for you is why do we need to do this course after having done ESO 204? So what more are we going to learn? So in this course, we are in general going to learn the mechanics of deformable bodies as opposed to rigid body mechanics that you may have learned in your first year, I think. Most materials are deformable, so when you apply forces to them, they undergo changes in shape or volume or both. And um, most materials will have to be analyzed using the language of the theory of elasticity uh, in order to figure out whether they are going to break or whether they are going to sustain the forces that you have applied on them. To do this, you need to formulate a boundary value problem for the body, pretty much like what you have done in fluid mechanics. And in some cases, you may be able to analytically solve the boundary value problem in certain simple cases, and in other cases, you will probably be using something like the finite element method or some numerical technique in order to solve the boundary value problem. Whatever you do, either you want to solve it analytically or through finite elements, you will need to formulate the boundary value problem properly. You would need to formulate the boundary conditions. You would need to formulate the governing equations, and that is what this course is going to tell you. We will also be adopting strictly a continuum point of view, which means that the discreteness of matter, we are never going down to the scales at which the discreteness of matter becomes visible. So for us, a body is a continuous entity and there is no discreteness involved, and this is part of continuum mechanics. This is in fact the first course in continuum mechanics of solids that you are doing. So there is a difference between what we are going to do here and what we have learned in ESO 204. In ESO 204, if you remember, you did not so much use the language of stress and strain fields. You did a little bit towards the end of the course, but mostly, for example, for beam bending, we would use the language of forces, moments, and displacements of the beam. This is typically a structural mechanics approach, um, which is which is very suitable for civil engineering structures, but we will replace it by a continuum mechanics approach, and this is sometimes this sometimes becomes not only useful, but it becomes actually imperative to use a continuum mechanics approach, as I will explain in the next slide. The third objective of the course is to learn experimental techniques to measure strains and stresses in realistic structures. That's the part that Professor Venkatnarayan will tell you about. So now I want to dwell a little bit on this second point. How are we going to build on what we have learned in ESO 204? What more are we going to learn? So let me take a simple problem that you might have solved in ESO 204. You must have solved in ESO 204, and that is the problem of a beam with a rectangular face, a rectangular cross section, which we have solved with something known as Euler-Bernoulli beam theory, which is a very clever structural mechanics approach to solving a beam problem. So remember what we did in that in that course. So the actual problem is a beam of this sort. It has a length h, depth of length of L, depth of h, and cross section is h by b. So it's a rectangular cross section. It can be other cross sections also. It's simply supported, and there's a load at the middle. The x and y axis are oriented like this, and from your knowledge of ESO 204, you would know that this x axis coincides with the neutral axis of the beam. Now, what Euler-Bernoulli does behind the scenes is it reduces this beam to just a straight line, and the straight line plus a cross-sectional area. This is what Euler-Bernoulli beam theory needs in order to solve this problem. What does it do? It tells you that the stresses are in the x direction. So there's only one component of stress which is in the x direction, and that stress depends on this famous formula that you have learned, my by I. So this m is the moment that is applied at any cross section, the bending moment at any cross section located at x. Y is the distance from the neutral axis, and Iyy is the moment of inertia of the cross sectional area about this plane, this axis. Okay, so all these things I can calculate from this picture. I can calculate the moment at any x from this picture. So the moment, you draw the bending moment diagram, which would be like a triangle, and you can find the moment at any cross section x. The distance y from the neutral axis is simply the coordinate y of a point as you go above the neutral axis. Iyy for this rectangular cross section is 1/12 bh cube. We all know that, and we can calculate that from a description of the cross section. That's why I'm saying that in order to figure out what the stresses in the beam should be, you need only this picture. This picture represents the beam as a line, which is basically the neutral axis. So the whole beam is collapsed into a line located at the neutral axis of the beam, and a cross-sectional area. That's all the information that you need. Further, for this simply supported beam, the maximum deflection obviously occurs at the middle, and this maximum deflection delta max is given by PL cube by 48 EI. You can verify that from your Crandall and Dahl. These formulas are given there. Now, this delta max is the deflection of the neutral axis. So deflection at this point in the y direction at the neutral axis. So for the Euler-Bernoulli beam, the structural mechanics approach, you don't have anything but the neutral axis and a cross-sectional area, and it is tacitly assumed that the sigma xx varies linearly with y. So you start here, sigma xx is 0, you go up, sigma xx increases in proportion to y, you go down, sigma xx increases in the negative direction in proportion to y. Okay, so that is what Euler-Bernoulli beam theory gives you, and this would be a very good. This is actually a very good way of finding the stresses in the beam, and this is very useful, very clever, and we will later criticize it, later look at it in depth, and even then we will not be able to deny the fact that this is actually a very clever theory. But let me look at a few situations when the information that we get from this theory is not sufficient for us. Let us look at the situation here. So Euler-Bernoulli beam theory gives you the exact distribution of the stresses. So if you go back to the previous slide, it tells you that the stresses are in the x direction and they vary linearly with y, and they depend on the moment, bending moment at that location X. So the stress basically varies with X as well as with Y, but the variation with respect to X is just based on this, on the bending moment that exists at a cross section at X. Okay. Now, what I have done here is I have done a exact analysis of this beam using the kind of theories that we are going to learn. We are yet to learn these theories. These are theories of elasticity that we learned. So I have used those in order to solve the exact stresses sigma xx on the face of the beam. What I have also done is I have plotted here as a map. We call it a contour plot, you might know. As a contour plot, what I have plotted is the difference between the exact stress that I calculate from a more accurate theory of elasticity minus what is predicted by the Euler-Bernoulli beam theory. So, 0 means that there is no difference between the two, both are same. 1 and minus 1 would uh, would mean that the differences are very large. So you don't have to worry about the colors so much. Just remember that this is the color that represents that there is no difference, and blue and red are the colors that represent that there's a lot of difference. So if you look around the neutral axis, then you see that it's mostly green. So there's very little difference between what Euler-Bernoulli beam theory predicts from its clever structural mechanics simplified approach and what the exact solutions look like. Both are very close around the neutral axis. But then you see a lot of red and lot of blue at the top and the bottom. We will do this experiment later, and you will see this with your own eyes that there are things happening that make the errors in this region and in this region very large. In particular, look at this part. You can see that it's very dark blue here. It's very dark blue right below the load, and that's where, and we will learn in this course that whenever you have applied a load on a large body, a concentrated load on a large body, you get a region of extremely high stresses around the point of contact of the force with the body. And this is an effect of elasticity that your Euler-Bernoulli beam theory will not be able to capture, because Euler-Bernoulli beam theory does not treat this beam as an extended body. It treats the beam as just a line concentrated at the neutral axis. So that is the difference. This is a region where the stresses will be extremely high, and as you can see, they would be much higher than what Euler-Bernoulli beam theory allows you to believe. And there's a possibility that due to application of this load, the beam may break from here rather than due to the Euler-Bernoulli. So if you just rely on the Euler-Bernoulli beam theory, you would get a good picture here because it's all green and differences are low. You would get a good picture here. Here also the differences are low, but around the application of the load and around the boundaries at the top and the bottom, you would probably overestimate or underestimate the stress by a very, very large amount. So what we have done is a full field analysis, whereas what Euler-Bernoulli beam theory tries to do is a structural analysis, a simplified structural analysis from which it tries to predict the stresses far away from where loads are applied, where supports are applied, etc. Far away from these regions, Euler-Bernoulli works well, but close to these regions, you may have situations where the stresses may be high enough to merit some attention. So this is the first example that I wanted to give you to explain why we need to go beyond ESO 204. The second example is a similar beam with a hole here. So there's a hole here in the beam, and if you go back to your Euler-Bernoulli beam theory, you will see that the Euler-Bernoulli beam theory actually has no way of analyzing this, because the Euler-Bernoulli beam theory deals with a line at the neutral axis and the cross-sectional area. There's no other information that goes into the Euler-Bernoulli beam theory. So the very fact that there's a hole somewhere in the middle, a through hole, uh, is something that the Euler-Bernoulli beam theory cannot account for. Now, if this hole does not, again we will do this in experiments later, if the hole does not lie at the neutral axis, then as you can see that the errors around the hole, the difference between the Euler-Bernoulli stresses and the actual stresses calculated by methods that we are going to learn in this course, that the stresses around the hole are very different. They are blue, so they are very different from what the Euler-Bernoulli theory makes you believe. So these are actually the regions where stresses are high. So these are regions where something might happen, the material might start failing, and so on and so forth from these regions. And so from an engineering point of view, it would be necessary to account for these regions. So it would be necessary to do a full field study of this beam rather than just be satisfied with the results from Euler-Bernoulli beam theory. So these were two examples that I wanted to give in order to convince you that we need to go beyond ESO 204, and that is what we are going to do in this course. Okay.